So we need to be talking about water very first up in this class because almost everything that we discuss later in the course will kind of center itself around what are interactions that are happening in water. All of the types of interactions we talk about, all the types of reactions we talk about take place in water, so we need to be very comfortable with this content. And I'm going to tell you right now, things that we learn today will stick with us throughout the course. It really forms like the central theme of this course, and we'll just see it kind of repeated in different examples throughout the rest of the semester. So in biological systems, there's more than just a bunch of water floating around, of course. We have many polymers, such as protein and nucleic acid, present in cells. We have salts and all types of ionic substances. And we have monomers and other small molecules. Think glucose. Think lipids. And many of these types of molecules are charged. And so things that are charged or partially charged is going to be something that we think a lot about over the course of this semester. So I will introduce to you Coulomb's law. It's possible you've already learned about Coulomb's law if you've taken physics. As chemists, we're going to use Coulomb's law to think about the interactions of charged molecules in a different way than you may have used it in physics. And if you look up the equation that you used in physics, it's going to look different than the one you see here on this slide. So, brief intro to the equation itself. Please do not focus on the equation. We'll focus a little bit about application of the equation later. And so that's what you're going to focus on. But for now, I'll just do a quick intro of the equation. So Coulomb's law describes the energy of association between two electric charges. And here are the two electric charges we're talking about, Q1 and Q2. U is the energy of association in joules. We can think about this as kind of attraction or repulsion. K is a constant. Don't worry about the constant. Don't really worry about the specifics of the equation. Of course, Q1 and Q2 are the charges. They will have both a value and a sign, right? So a charge could be positive or negative, and it could be 1, 2, 0.5, etc. R is the distance between the charges, and that is something we'll think about for sure, is distance. Finally, D is a dielectric constant. It's kind of related to polarity, but again, let's not worry about this. Okay, so let's think broadly about this equation. What do we know? We know Q1 and Q2 are the charges, and R is distance. So how should we use Coulomb's law in biochemistry? Well, if Q1, let's say, is 1, Q2 is, let's say, -2, and R is 1. If we look at what's happening here with the equation, we get -2 over 1. And so this number is equal to -2, right? For example, let's say that the denominator instead of 1 was 1/2. That would then change this to 1/2. 2 divided by 1/2 is now 4. So if the denominator is larger, if the distance is larger, you'll see that the value of this equation is smaller, right? When the distance was 1, u equaled 2, -2. When the distance was 1/2, u was -4. So in biochemistry, what we want to understand is that charges that are close together experience a stronger force of attraction or repulsion. How do we determine attraction or repulsion? Well, you already know the answer to this, right? If you've ever used a magnet, we know that opposites attract and similar charges repel. In the example I gave you, I had a +1 and a -2. Opposites should attract. What if I had a -1 and a -2? Well, similar charges repel, so we should understand that the attraction or repulsion has to do with opposite charge or the same charge. And I'll make this extra clear by putting that plus up here by the 1 for everyone to see. So we should understand from Coulomb's law this, that charges that are close together experience a stronger force of attraction or repulsion depending on their charge. Therefore, charges that are far apart should experience a weaker force of attraction. And here we're kind of talking about fully charged species, so ionic interactions in water, right? But I want to talk about more than just ionic interactions in water because we'll see kind of all types of interactions this semester. So I'd like to give you this table to kind of synthesize knowledge that you really already have coming into this class, but I think it's summarized very nicely. So this table shows us the bond energies in biomolecules, how strong, how weak. So of course, at the very top in terms of strength are covalent bonds. We're talking the sharing of electrons. Since we're sharing electrons, it's going to be the strongest type of bond. We won't really talk too much about covalent bonds in this class. In this class, what we talk about most are interactions. We're not talking about the sharing of electrons. We're talking about interactions between full charges, partial charges, or no charges. And so here is where I like to walk you through the types of interactions we need to be comfortable with in this class. The strongest type of non-covalent interaction is, if I can get my mouse down here, is the ionic interaction. So a full negative and a full positive are pretty strong, about 86 kilojoules per mole for that type of interaction. Now, this table doesn't have ion dipole, but I'll talk about ion dipole in this class a little bit. So I kind of slide it in right under ionic interaction. An ion dipole interaction is going to look like the interaction between one thing that is charged and one thing that is polar. So for example, we have this carbonyl functional group. That's ion dipole. That is going to be slightly weaker than ionic. Now what about the rest of these van der Waals forces? So we have the hydrogen bond, of course, and you should already know from previous courses what makes a hydrogen bond. That's even weaker. Then dipole-dipole, so two things with dipoles interacting. And then finally, London dispersion forces, where we have the interaction of two usually non-polar things. So they have no charge or no partial charge. Thinking broadly across this table, the things that have the strongest type of interaction are the most charged. Things with the weakest type of interaction are least charged. And so these are the types of interactions I want us to be super comfortable with this semester, and we'll get a lot of practice thinking about them.